Christoph, for giving this insightful talk. And we now all feel asking him a lot of questions. But unfortunately, that's not how it works. You will have an opportunity afterwards to directly ask him. Instead, we move on to Professor Hua Wang. Hua Wang got his Bachelor of Science in 2003 from Tsinghua University in China. He then moved to Caltech in California and got his Master of Science in 2007. He is PhD also from Caltech in 2009. Afterward, he was there as a scientist or postdoctoral scholar, also at Caltech for another year, and then moved to Intel as RF and millimeter wave design engineer. He was there for 1 or 2 years and moved to a company called Skyworks Solutions, where he was a staff engineer in 2011. From 2012 to 2018, he was appointed an assistant professor at Georgia Tech. He was there the director of the Georgia Tech Electronics and Microsystems Lab. In 2018 to 2021, he was promoted associate professor with tenure to the School of Electrical Computer Engineering at Georgia Tech. He was also engaged as the founding director of the Georgia Tech Center of Circuits and Systems. Now, since 2021, he is a full professor and chair of electronics at our department, the Department of Electrical Engineering here. The interests of Professor Wang are in innovating integrated circuits, hybrid systems for wireless communications, sensing, and bioelectronics applications. Hua, the stage is yours.
Okay, thank you, Ulrich, for your nice introduction. Thank you, everyone, for coming to my inaugural lecture talk, and good afternoon. So, in my following presentation, I would like to give you a brief overview of modern hardware electronics for future communication and sensing, in particular, how possibly we can build them to enable and support the beautiful systems that Christoph just presented. First of all, I would like to introduce my research group and the ETH, Integrated Devices in the Electronics and the System Group, in short, IDEAS. So we are focusing on integrated circuit design and the system implementation to address a wide variety of applications, including wireless electronics, biosensor, bioelectronics, as well as different emerging technologies. I want to thank all my team members, and without their support and collaboration, there's no way we can explore so many exciting research frontiers. All right, let's get to the electronics. We know that electronics are ubiquitous in our society right now, right? And they are extremely important. Why they are so important? Perhaps one of the major reasons is because the electronics and information, they are always going hand in hand. And we use electronics to acquire information from the physical world, which is called sensing. Electronics allow us to process the information, making decisions, which is called computation. At the same time, electronics allow us to transmit the information from one place to the other, establishing wireless communication link as well as synchronization, which is called wireless communication. So the application of electronics are essentially unlimited in our society. And we can see that some of the new applications include AR and VR, the quantum computing, IoT devices, wearables, as well as autonomous and driving. So it's fair to say that electronics are essential to the society and critical for the economy and strategic for the nations. In this talk, I would like to mainly focus on the wireless communication and the sensing electronics. Regarding the wireless communication, I'm sure many of you are familiar with the evolution of technologies for wireless technologies, right? The so-called evolution of the Gs. Back in the early 1990s to the 2000s, this is the time where we had 1G and 2G phones. The major functionality of those phones is to provide essentially voice calls. This is the time called mobile wireless communication. And in the 2000 to 2020, the mainstream is the 2G and the 3G and the 4G phones, where we'll have a much larger bandwidth, allowing us to browse the internet and the streaming the videos. This is the time called the wireless and the mobile wireless data. And the data consumption is the main topic here. If you look at some of the representative user cases from the Ericsson and mobility calculator, you can see that regardless of type of users, nonetheless, the video streaming is always taking a lion's share of the total data usage and per month. So what will happen to the future? What about the next 20 years? Right? It is envisioned that the broadband electronics, wireless communication electronics, together with AR/VR devices and advanced wearables and so on and so forth, will allow us to acquire a massive amount of data of the physical world, and eventually we can achieve the mobile wireless reality. Okay, so certainly a lot of data to support and for the wireless communication. How to support this large data rate? Well, here I'm borrowing one summary figure from Professor Studer's research, and which summarizes the spectrum allocation versus the carrier frequency and in the world. As we can see that if we want to have a larger allocated bandwidth in order to support larger data rate, we have to go to higher and higher carrier frequency. Right? This is the choice we have to make. But at the same time, we need to be clear about that there's another aspect we have to consider, which is called free space path loss. It accounts for the signal attenuation when the signal propagates wirelessly from the transmitter to the receiver. It can be shown that this free space path loss is inversely proportional to the square of the distance we want to communicate over, and also inversely proportional to the carrier frequency square as well. And so it's interesting that we can see that higher carrier frequency indeed will offer us a larger bandwidth and a higher data rate. But at the same time, they are facing larger, basically path loss, and we have to overcome. So overall, the wireless link has to be designed with a holistic view of the desired carrier frequency and the data rate, distance, as well as the power budget. Maybe we can put some numbers to the perspective, right? Let's say if I want to communicate using 1 gigahertz carrier and over a typical cellular network, maybe from 100 meters to 1 kilometers, the signal attenuation is a factor of 10 to the minus 7 to 10 to the minus 9. This is a huge attenuation of the signal. Well, if we go to a further distance out, for example, if we're looking at some LEO satellite communication, we need to send a signal from the Earth all the way to the satellite in the LEO orbit with 500 kilometers or 1,200 kilometers away. And in this case, let's say we are using a 15 gigahertz carrier and the typical Ku band carrier for SATCOM applications, and the signal attenuation will be 10 to the minus 17 to 10 to the minus 18. This is a substantial reduction of the signal. Right? So therefore, we can see that it is indeed challenging to communicate with high carrier frequency, large bandwidth over a long distance. Well, how to overcome these fundamental limitations? To do that, perhaps first we should understand the physics behind these limitations. Right? So in most of wireless communication nowadays, it is using something called omnidirectional communication, in the sense that the transmitter is sending out its energy equally to all the directions, and it's omni-radiation, right? So therefore, perhaps we can imagine that the radiation energy density will decrease over the distance while the signal is traveling away. Right? So in particular here, the radiation energy density, if we integrate it over the entire surface, in this case maybe a sphere, and due to the conservation of energy, this product should be a fixed value. As a result, and we can expect the radiation energy density should go down proportionally to the square of the distance, which is the relationship we just saw. Right? At the same time, the received energy by the antenna is a product of this energy density multiplied by the effective antenna cross-sectional area, and which is proportional to the square of the wavelength we are communicating at, carrier frequency, which is proportional to 1 over carrier frequency squared. So if we put everything together, we can see that this free space path loss can be quantified as this term, which is the product of the gain of the receiver antenna, gain of the transmitter antenna, speed of the light square, which is a constant value, divided by the square of this product of 4 pi times distance times the frequency. Right? So this is the problem. Well, since we know the spreading of the energy is the problem, the finite and the antenna area is also the problem. Can we do something to fix it, right? To to correct this problem? Right? The answer is definitely yes. For one of the example is to use the technique so-called arrays or beamforming. In this case, let's assume that we have n transmitter antennas and transmitter signals and launching signals with the same phase. And the electromagnetic waves will interfere with each other. In the far field, it will form the pattern that is behaving as a directional radiation, which will solve the problem of energy spreading, right? And moreover, at the same time, and since we have n element of transmitter transmitting at the same time, then total will have n times the energy. So combined together, it can be envisioned that, okay, using this n element transmitter, the receiver will receive power increased by a factor of n to the power 2, n squared. At the same time, if the receiver is also using this array technique, then the power will be further increased by a factor of n, so overall will be n to the power of 3. Right? This is called beamforming. It substantially boosts the receive power and can be used to overcome the path loss. At the same time, if we are able to provide some fixed phase offset among these transmitter elements or delay offset, it can be shown that we can actually steer the beam to other directions to communicate with other users. This is called electronic steering, which is much faster than the traditional mechanical way of steering an antenna and element. Okay? This electronic steering also allows us to rapidly track multiple moving users and targets. Is extremely useful. And for the receiver perspective, we can also steer our beam away from any possible interference to achieve spatial filtering of the interference. So overall, this is called electronic phase array systems. Such a system is being widely used in a lot of high-performance applications. One application is a satellite communication. Right? Remember, as we just discussed before, for LEO satellites, we need to establish a reliable link and over 500 kilometers or even like 1,000 kilometers away. Right? So we need to have some antenna and satellite payload. We also need to have some satellite ground terminals. So what is inside of these boxes? Many electronics. We can take the SpaceX LEO satellite payload as an example. This long thing is essentially the solar panel to acquire the energy, but if we look at the bottom surface, which is facing the Earth, immediately we will see 4 phase arrays right here. And we can also look at the ground terminals. These are the things we'll buy and install at the home. For the Starlink and the dish and the ground terminals, it is about 50 centimeter to 30 centimeter. If we open it up, we can see that immediately we'll see 1,000 the small patch antennas putting together in a 2-dimensional array. On the back side of this panel, we'll see hundreds of integrated circuits, ICs, operating together. Typically, each ICs will drive about 4 antennas or even 8 antennas, but to overall achieve this 1,000 element of array. Another example is the Amazon, which will launch their LEO satellite service as well. And in this case, their ground terminals is proportional, and the size can be scaled so that down to 10 centimeters as more portable devices, all the way to 70 centimeters for wideband and the connectivity and installed outside of the building. So overall, with the phase array techniques, satellite communication can be established, and we can provide broadband internet anywhere on the Earth without any infrastructure. Right. There are many other applications as well. For example, satellite internet IoTs, and in this case, billions of IoT devices can be connected to satellite with or without the gateways. This is very critical for mining industry, tracking and cargoes, as well as monitoring of critical infrastructures. And the satellite to phones, and this will allow us to call the satellite and making phone calls to the satellite through the satellites, and as an emergency call or emergency messages. Of course, other applications include the 5G and 6G wireless communication for broadband access, and the automotive radars and the radar for drone applications, as well as the imaging and the sensing for security applications, manufacturing, and food safety, food quality checking. All right, so many applications. What about the challenges? Well, and next I want to list several important challenges to see basically what is blocking us from now to the future next generation of wireless electronics. The first one is perhaps the output power. The output power of a wireless link typically is dominated by the transmitter or the power amplifier of the entire system. My group at ETH established and maintained this power amplifier survey, which accounts for the published the power amplifier designs and from academia as well as the industry from 2000 till now and across the different technologies. And in this plot, it summarizes the saturated upper power of the power amplifier versus the carrier frequency. As we can see that regardless of technologies that we are using, the saturated upper power will decrease monotonically over the frequency, which is more or less following the device Johnson's limit. Right? This plot shows us it's becoming more and more difficult to generate a high sufficient upper power over the frequency. The second one, the challenge, is the energy efficiency. And the energy efficiency of a wireless communication link will determine the total DC power consumption of the setup, and often for the mobile devices will determine the battery and basically life. Using the same survey, I'm plotting here the energy efficiency for CMOS devices and silicon germanium technologies over the frequency. We can see that from low frequency to 30 gigahertz, we'll have a great degradation of energy efficiency. Above 30 gigahertz, energy efficiency drops very fast. This is fundamentally due to the limited device gain at a higher frequency, as well as limited power handling capability at a higher frequency. Again, it shows that it's just becoming more and more difficult to design and achieve these high-performance electronics at a higher frequency. The third challenge probably is the complexity. If we just took and we just had the satellite and the terminal as an example, we can see that they typically should include 1,000 to 4,000 number of elements with hundreds of electronics and integrated circuits working together. Within each circuit, typically, we will also have multiple paths of signals. For example, 8 paths for the transmitters and 8 paths for the receivers. So all of these circuits have to work in a synchronous fashion so that the array can work properly. Right? Obviously, we can imagine that this puts a lot of this level of complexity, put a lot of challenges on the design, building, and operation of these large arrays. At the same time, it also will bring a lot of headache when we are trying to calibrate and maintain these arrays in practice too. Well, as a new research direction, AI and machine learning techniques are being and more used to build, synthesize these complex wireless systems, as well as achieve the smart and the fast operation and in practice. The fourth challenge probably is the latency. Right? And when we are using large arrays, each beam becoming very narrow. This is why we are trying to use it, because now we have higher spatial resolution. However, using these narrow beams to scan the entire field of view will take more time. Right? This is the trade-off. And this is particularly important for those applications that are supposed to operate in unknown and a fast changing environment, yet still requiring the robust wireless links. And recently, this application called drone racing and is gaining a lot of interest and popularity as a sports or as an entertainment. I'm showing a video here. Yeah.
Drone racing has everything that makes pro sports a big business. The competition.
Halo Walker gets the win!
The fans.
Absolutely incredible.
Yeah. A new application of electronics, and probably a perfect example of showing why latency really matters for these for this application, right? Operating in an unknown and a fast-changing environment, yet we need to provide very robust links. Okay. So, well, next, for the next several slides, I would like to present some of the research from my group and how we are trying to address these challenges. The first kind of example of research from my group is this autonomous beamforming array architecture. And unlike the traditional, more common arrays where the beam space is being computed in the backend, here we are trying to achieve some front-end analog computation accelerators for the beams, so that the phase differences, phase conjugates, and the beam forming can all be achieved right at the front end of the array. And this substantially accelerates the beam forming speed and it really cuts down the latency. So all these functionalities are being implemented in this, again, millimeter-sized tiny silicon chips. And as one of the measurement examples showing here is that, okay, when this array is receiving 2 signals at the same time, one desired signal, one interference, and without the beam forming and the notching, and we cannot really see anything because the desired signal is completely overlapping with the interference in the frequency, in the spectrum domain, and being corrupted. But once we enable this autonomous beam forming, and instantaneously, the undesired interference will be filtered out, and the desired signal will be boosted. and then we can actually demodulate the desired 64-QAM constellation. Overall, this technique will allow us to perform fast beamforming, steering, tracking of multiple unknown targets and the signal sources. The overall system response time is less than 1 microsecond, 1,000 times reduction compared to the state of the art. Again, it's very useful for these highly dynamic, low latency applications that often supposed to be operated in complete unknown environment. Another application, or let's say this example from my group, is this physical layer secured array. The goal here is to achieve a keyless, secured wideband wireless link. Right? It is known that a complex constellation, for example here a 64-QAM, can be decomposed as a vector sum of 2 or more simpler constellations, maybe 1 QPSK and 1 16-QAM. And we send these sub-constellations into the array with no delay difference. And let's also imagine the desired and the user, let's say Bob, is located in the direction that is perpendicular to the array. So when all the signal travel to Bob, it will have the same the delay. So then Bob can receive this sub-constellation and reconstruct the desired constellation seamlessly, right? But at the same time, we have some eavesdropper, let's say Eve, at some angle off from the main axis, and we can see that because the delay difference from the transmitter array to the Eve, and then the signal received by the Eve will be completely distorted, and this achieves the physical layer security without using any security keys. And as in some other functionality that are being implemented again in a very small silicon chip, we also built the antenna arrays and demonstrated the millimeter frequency. And we can see that in the case of the Bob, it can receive the signal with perfect EVM. And however, for Eves at the different locations, even just with only 2 degrees of difference from the Bob, and you can see the large degradation of the received constellation. Overall, again, there's no digital encryption, decryption needed, and the support and the gigabit per second of communication, no security key exchange needed, and overall, it's useful for those secured, low latency and limited resource applications. Right. Further, and we are looking at the array of operation in a dynamic way. Right? Typical arrays are being modulated by the phase or amplitude of all the array elements. And these weightings are typically not changed and kept constant during the beam operation. We don't change them. And this is called a static array, and which have its own limitations, but is widely used. So here, what we are looking at, can we use other ways in addition to modular array, and then achieve new functionalities? The answer is definitely yes. One of the examples is to use time to modulate array, and in this case, the simplest time modulation sequence is to turn on the array and elements basically sequentially in a less non-overlapping fashion. It can be shown that in this case, an n-element array can generate n+1 and the concurrent beams. And for example, 4-element array can generate 5 beams at the same time. This means this one transmitter array or receiver array can communicate to 5 directions at the same time, or performing sensing to the 5 directions at the same time. Right? It can be shown that just by reprogramming the timing sequences, we can change the number of beams from 1 all the way to n+1, and there's no hardware reconfiguration and a very low overhead, a very low complexity. This is very useful for one base station, immediately talk to many mobile users. This is also very useful for situation awareness radar in unknown environment. When we drop the radar in the environment, we want the radar to use the maximum number of beams it has to figure out the environment first, and then focus all the energy to one or a few beams to the interesting targets. Right? This is the situation awareness and radar. And we also demonstrated in a millimeter wave and a chip and a tiny chip, and with 4 elements, we show that 5 beams can be generated at the same time. And the array will be able to receive 2 instant concurrent signals at the same time. Right. One last example I want to show here is that other than using the time, we can also use the frequency to modulate the array as well. In this case, this is called a frequency modulated array. And it can be shown that the array factor now is rapidly time varying. It is a dynamic pattern depending on the time, number of elements, and the angle, as well as the distance. Further, it can be shown that using the time modulated array technique as the transmitter, if we have multiple receivers in the far field, each users will essentially see a distinct signature, which is related to with their angular location with respect to the transmitter. And in this case, only with one shot of signal and the transmitting, we were able to track and localize multiple receivers at the same time. This is very useful for base station and to establish links with mobile phones, and this is also very useful for example, traffic controls in autonomous driving. Of course, this technique can be used in radar applications too to achieve ultra-high resolution. Again, this concept has been implemented in the millimeter wave and the frequency and in a tiny millimeter-sized chip, and we design all the antennas and the supporting circuitry around it. And overall, we are able to demonstrate, indeed, in practice, that multiple users in the far field will be able to see complete different timing signatures based on which they immediately will know their location to the transmitter. And as this user tracking mode, it provides the sensitivity in the angle about ±2 degrees, and it also can be used as a radar mode that achieves 5 to 10 times better accuracy than the state of the art. Okay, so besides the research and the topics and wireless communication and the sensing I've been talking about today, we also work on other areas such as cryogenic electronics for quantum computing and quantum sensing, integrated silicon photonics for free space optical communication and LiDAR, new semiconductor devices for terahertz applications. We also have a long track record on CMOS bioelectronics and biosensors for point-of-care devices as well as drug screening applications. So with that, I think that's the end of my talk, and thank you for your attention.